Today we're going to start a very important section on velocity and acceleration. And if you are taking notes on this from my web page, you will need the handout that I give you. Otherwise, these notes will probably not make sense to you. And we're starting at worksheet 1. These handouts come from the College Board, the AP Calculus people that create the AP exam. And they're very good, and we're just going to work through it, and it's going to help us learn how velocity and acceleration relate in calculus. At the beginning, you'll see at the very top that in discussing motion, there are three concepts, okay, that we need to talk about. First concept is position. Okay, and when we talk about position, it is usually denoted with the letter or with the function label s of t or sometimes x of t. Okay, that's usually what the position function is labeled as. And the idea is the position function tells me where the particle, we're usually going to be talking about a particle moving along the x-axis. Okay, so we're talking about where the particle is located on the x-axis at a given time t. Okay, where is a particle located at a given time t? All right. Now, so the first thing is, where am I at? Okay, and that's the idea with position. Where am I at? The next thing that follows from that is velocity. I told you there's three concepts. The next one is velocity. Well, velocity, of course, it makes sense that we're usually going to call it v of t. But very, very importantly, velocity is the derivative of the position function. Okay? Velocity is the derivative of the position, or a lot of times I call it the location function. Okay? So you're going to see a progression here. We're going to go from position to velocity, and then we're going to go from velocity to acceleration. Okay? And that's the progression. Position, velocity, acceleration in just a minute. All right? Now, what does velocity tell me? Velocity tells me how fast the position is changing at time t. Remember, didn't we call that, when we first learned about the derivative, didn't we say it could be called the instantaneous rate of change? Okay, so here we see that showing up again. The instantaneous rate of change. All right? Now, there's something else, and I know you've learned this in your physics class, that velocity tells me. It also tells me the direction of movement. Tells me direction. Whether I'm moving to the right or the left, whether I'm moving up or down if we're talking about a falling object. Okay? So velocity also tells me direction. The third one that I've already mentioned is acceleration. And I already drew the arrow from velocity down to acceleration. And the reason I did that is because acceleration, which we will call a of t, is the derivative of velocity. Okay? So we have this progression from position to velocity to acceleration. It's the derivative of velocity, or couldn't I also say it is the second derivative of the position function? That's another way that I could say it. It's the second derivative of the position function. The other thing that velocity tells me is, that acceleration tells me, is it tells us how fast, now think of it, if it is the derivative of velocity, it's telling me how fast the velocity is changing, okay, at time t. Okay? Now, there's something else, though. There is a sign associated with acceleration. Okay? So the sign indicates if the velocity is increasing or decreasing. All right? The sign indicates if the velocity is increasing or decreasing. So we do have to pay attention to the sign when we talk about acceleration. All right? So now we're going to work through some true statements that are on your handout. Okay? So let's go to our true statement number 1. Okay, on the handout, I believe it says, if x of t represents the position of a particle along the x-axis at any time t, then the following statements are true. Now, before I do this, I need to probably give you a little picture, which is not part of this module. A lot of the AP Calculus questions about velocity deal with a particular particle, okay, and I'll just put a star here for my particle, okay. You have a particle, and what they're talking about is the particle is moving along the x-axis. So this particle is moving right along the x-axis. Maybe it's moving to the right, or maybe it's moving to the left, okay, but we're not talking really about, a lot of the time we don't talk about falling objects. We will have some problems that deal with falling objects, but a lot of times we're talking about a particle moving right and left. Okay, so you need to understand that when we talk about these true statements. True statement number 1. Initially means when time t is equal to 0. So when you see that word initially, the time is 0, okay? And that might sound like common sense, but we need to go ahead and identify it, all right? True statement number 2. At the origin means the position s of t equals 0. Okay, so if you see that phrase at the origin, then we're saying that its location, all right, the s of t is equal to 0. That's very important. Number 3, at rest. Well, if it's at rest, what do we know is equal to 0? Velocity. Okay, velocity is equal to 0. If it is at rest, the velocity is equal to 0. All right, now we get into some things talking about the signs, which are very important. Number 4. If the velocity of the particle is positive, then the particle is moving to the right. Okay, now remember, we're talking about a particle moving along the x-axis, okay, right or left. So I think you know the answer to number 5. If the velocity of the particle is negative, okay, then it's going to move to the left. All right? Or if we were talking about a falling or rising object, what would we say? If the velocity is negative, the object is falling, right? If the velocity is positive, it would be rising. Okay? Number 6. To find average velocity over a time interval, divide the change in position by the change in time. And we've already talked about this. And you may want to go over to the side someplace and write this down. Average velocity is much different than instantaneous velocity. Okay? Average velocity is just straightforward the change in distance which we can find with the position function over the change in time. It's still the slope song. Okay? It's still delta y over delta x. It's just kind of phrased a little bit differently. The change in position divided by the change in time. Okay? True statement number 7. Instantaneous velocity is the velocity at a single moment or instant in time. I think that one's already written out for you, right? Okay? Instantaneous velocity. I told you it was not going to go away. Number 8. All right, now let's talk about the sign of acceleration. If the acceleration of the particle is positive, then what's increasing? Velocity. Okay? Couldn't I also say it's speeding up? If the velocity is increasing, couldn't I say that it is speeding up? Okay? If the velocity is if the acceleration is positive, I could say that the particle is speeding up. Okay? And if you look at question 9, or statement 9, that makes sense. If the acceleration of the particle is negative, then the velocity is decreasing. Or couldn't we say slowing down? You may want to put that in parentheses off to the side someplace on your handout. Slowing down. All right. Number 10. This is very important. In order for a particle to change direction, then velocity must change signs. That is so important. Think of the particle moving on the x-axis again. Here's 0, here's the x-axis. If this particle is moving, let's say it starts here and it's moving this way, isn't its velocity positive? Okay. So for it to move back to the left, for it to change direction, then the velocity has to change signs. Okay, very important. Number 11. Number 11 says, one way to determine total distance traveled over a time interval is to find the sum of the absolute values of the differences in position between all resting points. Here's an example. If the position of a particle is given by, and I'm going to use S of t just because they use that a lot more. If the position of a particle is 1/3 t cubed minus t squared minus 3t plus 4. Find the total distance traveled on the interval for the times from 0 to 6. Okay? Well, now before we do this problem, I want to explain to you the difference between total distance and displacement, because the two are not the same. When we talk about the difference between total distance traveled and displacement, the two are not the same. And let's kind of look at it on the x-axis, since that's what we're talking about. If I had a particle that, let's say, it started at 3, okay? If that particle traveled to 11, okay? Now, isn't that a positive velocity, right? So it went 8 units, right? And then it moved back to the left 6 units. Okay? Back to the left 6, which we know would be a negative 6, right? So if it went to the left 6 units, isn't it at 5? Right? So my particle right now is camping out at 5. Now, let's talk about the difference between total distance and displacement. The displacement of this particle is 2. It's this. The displacement is 2. It is 2 units away from where it was. So in other words, we have to consider sign when we look at displacement. But when we look at total distance traveled, then we have to think absolute value. This particle went 8 units to the right, and then it went 6 units back to the left, but we think of that as an absolute value. The particle traveled 14 units. That's what the total distance was. Okay, the difference between total distance and displacement involves the signs. Okay, so now let's look at this problem up here. They give me this position function, all right? And if you look at the example I just gave you, we had to consider where it changed direction. Well, if I'm going to figure out where this thing right here changes direction, if you go back to your previous notes, it changes direction when the velocity is equal to 0. Where is velocity equal to 0? Well, the velocity is the derivative of position. So let's get to a new page here. The first thing I have to do is have my function 1/3 t cubed minus t squared minus 3t plus 4. This is the position function. The first thing I got to do is find the velocity function. So let's do that. S prime of t is going to be my velocity function. So using the power rule, we don't have to even use the chain rule on this one. It's going to be 3 times 1/3, so that'll just be 1. So it'll be t squared minus 2t minus 3. All right? So there is my velocity function. Well, now I need to know where it changes direction. So remember what we said, it changes direction anytime the velocity is equal to 0. So now we have a simple quadratic to solve. This one will factor very nicely. T and t, and -3 and +1. So we have two places where it changes direction. when t is -1 and when t is 3. Of course, we set both of these equal to 0 to find that out. Now, didn't our problem tell us that we were looking at what's going on from 0 to 6? Okay. We were told that we were going from 0 to 6. So there's one of those two I don't even need to use. I don't need to use this one because it is not in the time interval we're talking about. All right? So now what we need to do is we need to see what's happening with the particle. Well, what we're going to do now is we're going to check what happens at time 0. Now, what am I going to do? I'm going to use the position function. I need to know where I start. Where do I start? Well, when t equals 0, I'm going to use the position function to find out where the heck I'm at. 1/3 t cubed minus t squared minus 3t plus 4. I need to know where I'm at. So let's find that out. Let's plug in 0. S of 0 is going to be, well, this is going to be 0, and this is going to be 0, and this is going to be 0 plus 4. So it looks to me like my starting point is 4. This is where I start. My location is 4. Okay? This is my location. The location is 4. Now, didn't we know that there was a change in direction at 3? Right? So let's find out how far we traveled. Let's find our change in position up to that point. So now let's do S of 3. S of 3 is going to be 1/3 3 cubed minus 3 squared minus 3 times 3 plus 4. So 3 cubed is 27. 1/3 of that is 9. So I have 9 minus 9 minus 9 plus 4. All right? So these two are 0. So I have -9 plus 4, and I'm at -5. This is my new location. So let's slow down here for a minute because this is all new, and I want to make sure you understand what's just happened to this particle. Where did I start? I started at 4. So let's think of this on the x-axis. Here's 0, 1, 2, 3, 4. The particle started right here. Now, where did it go from time 0 to time 3? Didn't it go where? Now, wait. This is its location. It went over to -5. 1, 2, 3, 4, -5. So now my particle is sitting right here. So how far did it travel to get there? 9 units. To the left, right? It traveled 9 units to the left. And that is its location at time 3. Okay, its location right now at time 3 is -5, and we know it's going to start going back to the right because this was where the velocity was 0. So now the only other thing we need to find is S of 6. The other end point that we're talking about, because we were told to look at it from 0 to 6. So now we're going to do S of 6, which is 1/3 times 6 cubed minus 6 squared minus 3 times 6 plus 4. Okay? So 6 cubed is 216, right? And isn't 216 divided by 3 is 72. So this is going to be 72 minus 36 minus 18 plus 4. 72 minus 36 is 36. 36 minus 18 is 18. 18 plus 4 is 22. That is my final location. Okay? This is my final location. So now, and I don't have quite enough room to do this to scale, but my particle is way over here at 22. It's way over here. So didn't it move 27 units to the right? All right. So it moved, use a different color, it moved 27 units to the right. Okay? So, what is the total distance this particle traveled?
32.
It traveled 9 units. Now remember, we don't care about the fact that that was in the negative direction. Okay? It traveled the absolute value of -9 plus the absolute value of 27. It traveled 36 units. That is the total distance. All right? And that completes worksheet 1, and that is where we're going to stop for today.